Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. Today we are going to continue on document stores. I don't know if we will finish everything, but I'll go as far away as we can. So just as a quick reminder of what this is about. Document stores are a bit like relational database systems like PostgreSQL, except that they can manage data that is nested, possibly highly nested, and heterogeneous. It means that you can have tables in tables in tables in tables, which in JSON would be arrays of objects, and you don't need a schema, right? That's a huge difference with the relational database management system, that you don't need the schema. And the way it works is that we have thousands, millions, billions, trillions of documents. The documents shouldn't be too big, typically up to 16 megabytes in many of the systems. And it can be JSON, XML, so there's different kinds of document stores, but the principle is the same. It's collections of trees, also known as denormalized datasets, denormalized tables. Okay. We saw that another major difference for many of these systems with relational database management systems like PostgreSQL is that many of them do not have a query language like SQL or a language similar to SQL. And instead, they provide you with an API like this. In that case, it's the JavaScript API. And the idea is that you write code programmatically in another language that's a host language, can be JavaScript, Python, Java, and so on. And in that language, you have some API, application programming interface, that allows you to interact with the system. And then you can have an iteration through all of the trees that you get as a result, right? So what's important is that this is all nested in some other programming language to interact with the system. Some document stores do have a higher level query language, but that we will see next week, all right? So I showed you in the case of MongoDB that since it's an API is not as nice as a query language, but I showed you how you can do a selection, a projection with the equivalent SQL query. I showed you how you can do the order by, the limit, and the offset of SQL. This is how you do it. It's functional. Again, you can swap the order. It doesn't matter in what order that is, the sort, the skip, and the limit. And what about grouping? Grouping is slightly more involved in terms of API compared to just a group by in SQL. But in fact, the way it works is very, very similar to MapReduce and Spark. And this is the reason why I don't need to tell you much about that, because the idea is that it's exactly the same idea of creation, transformation, action, getting the results. And you have your stages there. It's just a list of the transformations you apply. Of course, it looks different than Spark, but logically, it's really the same idea, right? So all you need to do is look at the documentation, and you will have absolutely no problem doing that sort of things, since you already know MapReduce and Apache Spark. But of course, it would be much nicer to have a query language instead of these two. That would make things much more easier. One way you can see that is look at all the curly braces you need, all the dollars you need. You know, that's just a lot of tough things to write in terms of productivity. Now, how do we modify the data in the sense of update, insert, and so on, like we can do in PostgreSQL? That's the difference with Spark and MapReduce, right? In Spark and MapReduce, we cannot do this because this is just a data lake. So you throw the data in there and just read it. But since I told you that this one is on the light side of the force of the ETL-based systems where you import data, you can also modify that data. So there is an insert one that allows you to insert one document. There is also an insert many. So you can also insert plenty at the same time. There is also an update many and an update one to update just one document or many documents. Here I'm setting the century to 20 wherever last is equals to Einstein. It's similar to the update SQL. There's an update query in SQL that does something similar. So again, you have update one, update many, and you have delete one and delete many in order to delete records that match a criterion. So here you would delete from the collection scientists all of the documents that satisfy the criterion here. The syntax for this, the selection criterion is the same as you have in Find, right? That's the same way you select those that you delete or update. Okay. Scientist, again, is the name of the collection. If the collection has a different name, then you're going to have something else, but DB is always DB. Okay. Now, what about the atomicity? Now, we've already talked about that in the context of acid properties, consistency, and so on. You know that in a relational database systems, you have acid, right? So atomicity, consistency, isolation, and durability enforced through transactions. Now, in document stores, it's not as strict on acid as in other systems, and it comes from the scale-up, the fact that we need large collections, possibly distributed. So we are not quite at acid yet. People are working on it. However, what we do have, and what MongoDB guarantees you, is that only one person at a time can touch one document. It cannot be that several people are touching the same document. But you could have Alice modifying the document right here, and Bob modifying the document right there in the same collection. That's entirely possible. So this is the granularity of atomicity. One document, it's easy to remember because it's just like in HBase, where the granularity is one row, right? And a document logically would correspond to a row. So, that's how you can remember it, right? So the granularity is one document. Now, I talked about languages. I'm just briefly going to say that there are languages out there that can deal with nested heterogeneous data, just like SQL. The one we look into is JSONic because it's almost all based on a W3C standard, which is called xQuery. But there are others. There's Uncle, there's Particle, there is GraphQL, and so on and so on and so on. So all of these languages, there's every couple of days there's a new one because people still discover they need a language, but they forget to look at the ones that already exist. But hopefully one day it will consolidate, and there will be just like SQL. SQL is there is nobody disagreeing with SQL for tables. That's the only language in town. But for collections of trees, document stores, it's not. It hasn't yet consolidated. All right, but I teach you one, and then you can learn any other language easily. So now a few words on the physical architecture, what we have inside. So I'm going to say a few things that are not going to surprise you because this is things that we've already seen in many systems. The first thing that's not going to surprise you is that we have replication, meaning that every document is not stored just once, but actually 3 times, and you can even change that, maybe more. So it's just like what we had in HDFS, where we replicate the blocks. So that shouldn't surprise you, right? We just replicate. And the other thing that is not going to surprise you is that we also shard the collections. But this is also not surprising because this is in the same way that we have the blocks in HDFS, the splits in MapReduce, and so on and so on, right? So we just partition the data. And so we have this 2-dimension, right? 2 dimensions, we replicate and we partition. So this is what we get. And the partitioning by default is done on this object ID, this ID underscore ID that I told you about, but we can change it. If you have you have a list of people with a social security number, you can ask that the partitioning is based on the social security number, right? All that start with a 0 are in the first one, that starts with a 1 in the second one, and all the way to 9, and you have 10 partitions. That's an example, right? The name of a shard or a partition is called a replica set, right? Because it has several replicas of that shard. We call it a replica set. More exactly, what we call the replica sets, it's the machines that host the copies. Now, the architecture is not the same one as in MapReduce, Spark, HBase, HDFS, and so on. It's a different architecture. It's not that you have a single coordinator node and worker nodes connected to it. Instead, we have this decentralized architecture in each replica set. This is just one replica set, maybe the one from F to P, for example. And then you have a primary machine, and then a few secondary machines. It's not going to be 1,000. It's more like 3 machines in that case. Each machine hosts one replica of the shard that is sitting on it, right? So it's called primary and secondary. Typically, people communicate with the primary machine, and the secondary machines are only there in order to host the replicas. But if you have a lot of people connected to the system, you might also allow people to connect to the secondary machines, right? At your own risk, because you might have differences in data if it has not synchronized yet, right? So you might have, because of the CAP theorem, It might not always be extremely consistent, right? So this is a replica set, and we have as many replica sets as shards. Actually, now it's even enhanced in the newer versions. You might have several shards on the same replica set, right? So it's even more flexible than it used to be. If you oversimplify things, one shard on each replica set, and in reality, you can actually flexibly allocate the shards to the replica sets, a bit similar to the way you allocate tasks to slots in MapReduce and Spark, right? So this is the way that it works. It even gives you control. If for legal reason you have to have some data in that data center, some data in that other data center, you can even say which partition of the data is allowed on what replica set. So it even gives you control of that. But basically, the data is spread over these replica sets, and you again have a primary in every replica set, and the secondary is connected to the primary in every replica set, right? And then you have some central place that coordinates the whole thing that people connect to, right, for MongoDB. All right, now, what about the way we write things? And this is different from relational database systems because, again, we have to replicate the data. What's going to happen is that somebody issues a query, maybe insert one or update many or delete one, or I don't know. And it's going to write to the primary and then propagate synchronously, blocking call, synchronously to some machines until you reach a certain threshold. Now, let's say it's 3. So now I have 3. So now I say, OK, now it's over. I return to the caller. The synchronous part is done. And asynchronously, I continue to replicate in the background, right, to more machines. But there is really a synchronous part and then an asynchronous part. It's just like in HDFS, in fact. It's exactly the same idea, right? You synchronously replicate to the minimum replication, and then you give the control back to the caller, and you continue to asynchronously replicate in the background. Okay, this is called the write concern. I have no idea why it's called that way, but it really means that you don't wait until it's replicated everywhere. That's the reason why it's only eventually consistent, but not fully consistent, right? So it's, yeah. Oh, yes. Okay. Zoom kicked you out. Yep. And you are here with a causes again. There you go. So, all right. So yes, the write concerns. So we are basically AP, but not C. All right. Even though with partition tolerance, you could argue that you still need, because of this, it's only partition tolerant to the extent that you can access at least one machine in every one of the replica sets, right? So that's always to take with a grain of salt. Okay. Okay. Now I'm going to explain to you how, because we are on the light side of the force, we can actually have quick lookups, quick queries that return in just 1 or 2 milliseconds. It's amazing. You can have billions of objects in your collection, and you have a fine query with a specific criterion that returns one object. It's almost instant, 1 or 2 milliseconds. There's no way you can achieve this with Spark or MapReduce, right? Even if you use a filter transformation in Spark, it's not going to be done in 2 milliseconds. But in MongoDB, it is the case. And in PostgreSQL, it's also the case. This is because the systems that do not work as data lake, but the systems in which you import the data, meaning the system has control over the storage of the data hidden from you, data independence, then you have a fancy feature called indices. Indices are exactly what you have at the, who knows what an index is in databases? Who never heard of an index in databases? Who doesn't know if they ever heard of an index in databases? Who doesn't know if they heard of an index? Okay, you're shy. Okay, so you probably, for sure, have seen an index at the end of a book, right? So at the end of a book, it's common to have an alphabetical list of all the words, the keywords that you have in the book. And then you look it up alphabetically, and you know how we do that with binary search, right? You just look, you learn that in primary school, how to look up a word in a dictionary, and then it tells you the pages on which the word is. Who has already seen that? Okay, that's all of you. Indices work exactly in the same way. This is exactly the same way. We need to build an index structure like this. It's not going to be words. It might be integers or other values. But the idea is that some queries will be very highly specific, like find name Euler is just that object right here. Some others might be less specific. So this is called a point query. This is called a query that's not highly filtering. If we ask for mathematicians, we might get thousands or even millions of people in there. But the indices, they are good for this kind of queries. They can accelerate those that are point queries. There's another kind of queries that's called a range query, where we look for an interval. For example, all the years after 1900, it can even be between two numbers. This is called a range query, right? So point query, not highly filtering query, range query. This here is just a way that database people think of the queries. And the only way we call that point query and so on is that it has an impact on performance and on the indices that we are going to use. Indices is the plural form of index, by the way, just like matrices for matrix and so on. But some people say indexes, so you might hear the two. So how can we make this query super fast? Because again, with Spark, this is going to be slow. You need to scan through the whole data set in order to find these documents. So how can we make this super fast? Well, we use indices. And the idea is that we have a collection of billions of objects. In that case, there's only 5 because that's all I could fit on that slide. Imagine that we want to accelerate looking by color. If I want to very quickly retrieve the fruits that have a given color, I need to build an additional structure. It's something that doesn't otherwise exist in your system because all you store on the disk is this. But if you add another structure like this, where you have yellow, orange, red, green, brown, and then you have the pointers, in memory is instant, that points to the objects with a specific color. For example, green points to the kiwi and the apple. That's an example. This is an additional structure in the same way that the index in your book is also additional pages at the end, right? So this is something supplementary that you need to do. So now I'm going to tell you how that structure actually looks like in practice. Okay. Now, the first kind of index is called the hash index, and the second kind of index is called the B3 or B+3 index. So I'm going to show you the two to give you an impression. And by the way, these indices also exist in PostgreSQL or in relational database systems, right? They are not even specific to document stores, but they are very important in document stores. All right. So imagine we have this, and we would like to index on the century because we want to accelerate the point queries or the lookups on the century, right? We can actually ask MongoDB to do it. You don't need to build that yourself. You just issue that command right here. Magic formula is create index, century hash, to tell MongoDB you want a hash index on century. And this is what's going to happen. And again, you don't have to do it because MongoDB does it for you. So once you have issued that command here, it's going to build a hash table. And a hash table is basically a huge array like this, where you can put the values of the century key, and you can put the records, it's just the pointers to the records corresponding to this, right? Now, how does that work? We use a hash function. Hash functions come from cryptography, right? So it's from the beautiful world of cryptography. It's basically, it basically turns every number or value into some smoothie, basically, which is basically a small integer or an integer. It's like a mixer, and you just press the button and you get something out of it. So this is what is H right here. And it has a few properties, cryptographic properties. One of the properties that it has is that it looks a bit random. It's deterministic, right? If you feed 20 here, you will always get 0. So it's deterministic, but it looks random. And the reason it looks random is that it tends to distribute a little bit all over the place, the integers. It's very difficult to reverse. If I tell you 0 and you need to give me back the values for which H is 0, it's very, very hard to do. That is one of the assumptions behind hash functions. And this is why it's actually useful in cryptography, because the fact that it's hard to do makes it harder to decode. And in fact, the blockchain for Bitcoin relies on this as well, because the whole Bitcoin blockchain relies on the fact that it asks you to revert the hash function and to find a value such that the hash starts with a certain number of zeros, and the higher the number of zeros you ask for, the tougher it gets. So this is how you adjust the difficulty level. But anyway, in that case, I have this hash function, I call it h. I'm not giving you the formula. You can do simple things with just multiplication, addition, and modulo typically, but you can have also more complex approaches. All I'm saying is that when I put 20 into my mixer, I just get 0 out of it. So what I do is that I put 20 at position 0 in the array, assuming I start with 0, and I have a pointer right here to the object with 20. Then I do the same with the second record, because again, I'm building my index. So the second record gives me 20. Oh, I thought I had corrected that. I'm not sure why it's back. It was supposed to be stored as, pretend it's 20 in there. I just overlooked it. Then century 19. So imagine that h of 19 gives you 4. Then that's at position 4 in the array. And then I add my pointer. Then I have Euclid with century -4. And h of -4 gives me 3. -6 gives me 1. 20, it's again there. Now I have my index. Some of the cells are empty, and that's totally fine. In fact, it has to be, because you need to have an array large enough to avoid collisions, because that's another assumption you make about hash functions, is that they don't collide so easily. Collision is when two numbers get you the same position. You want to avoid that. In practice, you can't. So in that case, you would just collocate several values on the same row and just add an additional structure to disambiguate. But to simplify things here, I'm assuming there are no collisions, right? But some cells are left empty. And so what happens then if you want to find the scientists, let's say in the 19th century, you take the 19, you call h, it's the same function h, it's a given, you just select the same function h, it gives you 4, so you know you need to look at position 4 here and follow the pointer, and that's it. What's the complexity of this? Of looking up the record with the query? Go ahead. O of 1, exactly, O of 1. It's magic. O of 1, H is O of 1. It's just a bunch of plus and multiplications. Looking up a position in an array is also O of 1, right? You have pointer arithmetics in languages like C, C++, because that's every row has the same size. So you directly go into the memory at that position. And following the pointer to the record is also O of 1. So it's magic. It's almost magic, right? You just in O of 1, it doesn't matter how many documents, it's instant. You immediately get the results like this, right? But of course, even though it's magic, there are a few limitations to the whole thing. The first limitation is that it's very good for point queries when you're looking for a specific value, but it's not good for range queries. Why do you think hash indices are not very good for range queries? Imagine that I'm looking for all the people between the 10th and the 18th century. Yes? Yes, exactly. So we would be forced to look one by one all of the values in my interval 10 to 18, and every time ask for the records. The reason we have to do it, we would have to do it, is that the distribution of the way that my h function distributes these values in the array looks random. So these values 10, 11, 12, all the way to 18, they will not be at the same place. They will not be, roughly at the same place. They will be all over the place. So there is no way you can actually execute range queries, except if you accept to go through each one of the value of the interval. But if here it's integers, so you might do it. But imagine if it's doubles or real numbers, there's no way you can do, you can go through the values one by one. That would be impracticable. Yes? Oh, because this is hash indices, but you're absolutely right that we can make them consecutive, and this is the B+3 indices. So that's a great transition to what we are about to do. That's exactly the trick. You need to make them consecutive if you want to support range queries, right? That's because you don't know in advance what numbers you're going to have, right? It must be able to index anything. If you knew in advance the values of century and you know it's only the numbers -20 to 21, then in that case, of course, you could build a spatial structure that does it that way. But in general, you don't know. So you have to use the hash function. And it might also be here it's integers, but what if it's strings or dates or something else, right? So in that case, the hash function maps to an integer that you can interpret in a position in an array, right?
Why?
No, go ahead.
Yeah, right. The complexity of creating this is basically like looking up is very easy because creating this.
So what's the complexity of creating this? What is the complexity?
You have to scan all the
So is that O of linear? Yes, exactly, O of n. Yeah. So you're right. The complexity is O of n.
So what did we win here?
What did we win? It's not that we win. It's not a free lunch. We traded something for something else. What we did is that we paid something. It's a cost of building the index. That has a cost. In fact, it can take hours for MongoDB to do this. So either you can wait or you can let it do in the background. So it takes hours. But what you get back from that cost is that when you arrive on your website and people visit your website and you want to query, then it's instant, right? But it's not a free lunch. It's instant because you paid before with the building time, building all of that. You paid in the building time and you also paid in space because that also needs space on your machines, right?
So it's about creating useful indices for later.
Exactly. And this is an art and a science. That's exactly why it's so important in document stores, because when you use a database or a document store, you need to anticipate on what you believe people will do. Sometimes you know because it's your code, right? If you build the code for the website, you know what kind of queries are going to arrive. And based on that, you can build the indices that you believe you need in order for your website to be fast. But it requires some thinking. You really need to take the time of understanding this. You need to also look at the space you have because you might think, okay, let me build all the indices I can possibly imagine. But no, it doesn't fit on the hard drive if you build all of them. So you have to make a selection of what you need to index, right? But your intuition is good. And that's a great transition for the B+3s because exactly in the B+3s, we are going to put them such that the intervals are preserved, right? There's also a problem with the hash function is not perfect in real life. So you might have collisions that force you with extra structures and that might slow down a bit the lookup. And if you want to avoid collisions, then you need a huge array, but again, you need to pay it in terms of space. So it costs more money in terms of hard drives, right? This is why we have another solution that's also used in relational database management systems called the B+3s. And the B+3s, like their name indicates, use trees, but nothing to do with JSON or XML. It's good old trees that you see in theoretical computer science lectures. And the reason why the trees look like this is that when we access the disk, because the index is going to be stored on the disk in the end. Part of it might be in memory, but on the long term, it's stored on the disk. When you access data from the disk during the index lookup, you read in blocks from the disk, right? You never read just a few bits from a disk. Always a whole block, something like 4 kilobytes at the same time. So we try to structure the nodes of our tree in such a way that it's roughly slightly below 4 kilobytes, just so that it matches the disk blocks. And again, because we are aware of the hardware that we have below that, right? So this is why we structure it in that way. Now, this is, you probably remember from theoretical computer science, the way that it works is that here, that's an alphabetical lookup. Everything that's before this in the dictionary is on the left. Everything that's above this is on the right. Here, everything before com is here. Between com and is in the dictionary is there. Between is and merely is here. And after merely and before possess is here. So it's all nicely organized in this way so that we can look up. How much does a lookup need? By the way, what's the complexity of a lookup? O of n, O of 1, O of? Log n, exactly, that's logarithmic. It needs a logarithmic amount of time. It's basically the depth of the tree, which is logarithmic. If it's well balanced, it's logarithmic in the number of nodes. Okay, now there are a few constraints on B+3s. Typically, the leaves are at the same depth always. You cannot have something that is a bit, that have multiple depth, all at the same depth. and there is also a convention on the size of the nodes. In that case, an example of convention is that the nodes, not the leaves, right? The ones that are not at the leaves, they have between 3 and 5 children. 3 children, 4 children, 5 children, but not 6, not 2, right? Between 3 and 5 children. The only exception is the root. The root can have less. It cannot have more, but the root is allowed to have less children. The minimum would be 2. I mean, if the root only has 1 child, then it's useless, right? So then you would remove it. Okay. Just a word of warning. B+ trees are not standardized, meaning that if you try to look that up over the internet or look at university textbooks from other universities or even the way it's implemented in systems, there's many, many different ways of specifying the B+ trees. We are not going to implement any also because it's very involved, very complex. So what I did for the purpose of that lecture is that I picked a convention that I'm using and we'll just stick to it, which is that we have a parameter D and we say that the number of children is between D+1 and 2D+1, right? In that case, I picked D equals 2 and that gives me between 3 and 5. Do I have an example? No, I don't. So if I take D equals 10, for example, then that gives me between 11 and 21, right? But there are other conventions. There are people who say between D and 2D. There are people who say between D+1 and 2D. I mean, there's all kinds of ways of doing that. So let's just pick D+1 and 2D+1. And some other people do not specify the number of children, but they specify the number of keys in a node. So for example, instead of saying that there are 4 children, for example, instead of saying there must be between 3 and 5 children, they would look at the values instead, right? And they would say there must be between 2 and 4 values in here. So here it's 3, so that's fine, right? But again, in that course, when I specify the interval, it's on the number of children right here that must be between D+1 and 2D+1. That keeps things easy enough for us. But just be prepared to the fact that not everybody agrees. And the values, because it's a B+ tree, are at the leaves, right? So the actual keys, the keys for the index, it's actually the values in JSON, they are right here. That would be all the values you see in your collection. And they are in an order, right? You see it's always an alphabetical order here. It would be an increasing order with integers. So these are the values in blue. The values right here are only for the lookup. This is only to help you go left or right in order to do your search, but the actual values are all in the blue zones here. And it's very common to reuse, to take the values that we put in here, we just copy them over, right? So in that case, I just pick the first value that comes, I put it here. The first, I put it here. So this is, you just reuse them. You don't have to invent some extra values. All right, so it's just a B+ tree. This is what it looks like. And again, a word of warning, because when I told you, if I say between 3 and 5 children, it means between 2 and 4 values, it's because of this. If you have N trees, and here I mean real trees in the street, planted in the streets, how many intervals do you have between the trees? And -1, right? If you have 3 trees, then you have 2 intervals between the trees. So that means that if you look at the number of children, if I have 4 children here, then I have 3 values, com, is, and merely. These are 3 values for 4 children. So you need to be careful of that -1 when you count the number of values, right? So in particular, when I say that the number of children is between 3 and 5, it means the number of values is between 2 and 4. And when I say the number of values is between 2 and 4, it not only applies here, it also applies right here, that the number of values is between 2 and 4. You just need to do -1 and -1. For whom is that clear? Okay, awesome. So this is yet what I've just said, right? 2 keys, 3 children, 4 keys, 5 children. Again, key here, what we call a key is in the context of an index, right? It wouldn't be a JSON key. It's just, we call it key because it's in the index. But the keys that you have here are actually the values you find in the JSON that you're indexing, like the centuries, for example. And now I have an animation for you to show you how that thing works. So when I start, imagine I'm building my index. For simplifying, I'm assuming that the values come in increasing order. In reality, it's not going to be the case, right? It's going to be just totally random. It's just to simplify the animation, just to show you how that works, that I'm going to make them arrive in increasing order. But it's specific, it's a specific case. So here, we have a first value 1, we just add a node and that's it. Then I have a second value 2, then a third value 3, now I just have one node, and then I have 4. And now I have more than 4 values because I said I wanted a 3, 5, b plus 3. So the number of children is between 3 and 5, meaning the number of values is between 2 and 4. So now I have a problem. That's not okay. I cannot have 5 values. What do? I split it like this, right? Now I add one depth, one level to the tree, and I have a child on the left and a child on the right, okay? Now I keep adding more. It's okay for the roots to have less children, by the way. That's why we only have 2 children here. It's the roots. Now I keep adding numbers, still between 2 and 4. Oh, I have a problem again. I need to split. What do? I just split it like this, taking 7, and I can just add 1 to the upper level, right? Now I have 3 children of the root. Who is following? Okay, great. So now I continue to add some of them, 10, 11. Oh, I need to split again. There you go. Right? It's beautiful. It just grows like this elegantly. You just keep inserting. Now now I fast forward a little bit, and I'm all the way to 16 values that are nicely indexed like that. And now I have a depth of 2, right? I have 2 levels, or a height of 1, depending how you see it. Now I add 17. That's too much. Cannot be 5, so I have to split. But look, now I'm propagating the problem to the root because now the root has too many children. How many children? 1, 2, 3, 4, 5, 6 children because of the 5 values. So I also have to split the root, and now I'm at 3 levels. So you see, as you keep adding and adding and adding value, the number of levels is going to increase, right? So in that case, it's in order. You can also insert values in the middle without any problem. So that's the idea. So if we do it for this specific collection right here, let's do it. I create an index that this time I say century 1. 1 is the same one as when I sort. 1 means ascending, -1 means descending, right? I can control if I want my index to sort in ascending or descending order. So if I say century 1, it's in ascending order. So now I just build my tree in order of in which the keys arrive that I consume them. So 20, then 21, then I have 19 right there. Oh, I need to split it. I picked a different parameter because there are so few values in there that now I just don't want more than 2 values per node, right? So I split, then I have -4, again, I need to split it again, then I have -6, I need to split it again. No, I reorganize. You can also just shift this one over, then that's fine. You have your constraint fulfilled, and then 20. And now comes your query. Now it's a range query. You see the $GTE. What's the complexity of the lookup? O of log n, exactly. I just go down the tree like this in logarithmic time, I find the node. Now in practice, the number of children and the number of values per key is not going to be a small number. It's more like 1,000 or a few hundreds, right? So you can really have a lot of values in there in practice. But for the PowerPoint, I just picked low numbers. Okay, and that gives me the range query, you see magically in logarithmic time instead of linear. Linear would be if I had to scan everything with Spark. But here, in logarithmic time, I get all of these answers, right? Now, MongoDB is nice with you because it gives you an index for free. That's the index on the underscore ID field. That one, it's a B tree, a B plus tree, and it's always there. You can always look up in 2 milliseconds any object with its underscore ID. Makes it very convenient. If you want indices on other fields, then you need to ask for them. And the way you ask for them is with this create index thing here. That's how you create the indices. Now, if you create an index, you can do it in 2 ways, and it's your choice, technically, how you do it. The first way is to tell MongoDB, please build that index. You have the whole computer resources for yourself, and I'm coming back in a couple of hours, and nobody is going to have any queries. That's called synchronized, so it's blocking, right? You just stop the database completely and build the index, and when it's done, you can use the database system again. There is another way that's telling MongoDB, you know, I would like you to build an index, but I still want to continue to use MongoDB. So in that case, it's going to build the index in the background. So you can continue to use the database, but it's going to be slower because some of the resources are used to build the index. And of course, the index is going to take a little bit longer to build because you're also querying at the same time. So you have the two options, and it's your choice, right? Which one you want. And then what happens is that if you modify the data, the cost of modifying the data is slightly higher because whenever you modify the data, you also need to slightly modify the index to adapt it to the new data, right? So this is also a cost that you have when you add new data, and you get that back as faster queries. So basically, if you don't have any indices at all, and you have a query, it's just like Spark, meaning that you have no choice but to read the entire data set from the disk, everything, and you just apply the predicate to every document, and you filter all of that in memory, linear time. If you have an index, then the index will allow you to directly fetch some of the records, but not all of them, because the index, imagine it's a range, so it's going to just return the records you need. So then you're much faster. It's going to be in O of 1 if it's a hash index and it's not too many records. It's going to be in logarithmic time if it's B+3, but it's better than linear. Now, in some cases, you're done, but in some other cases, you're not quite done. In reality, what often happens is that the index is useful to accelerate a bit your query, but you still have some work to finish in memory after you have used the index. So in reality, you really need to do both. You use the index plus you do extra work in the memory. And I'm going to give you a few examples here. Imagine I create a hash index on name last, right? So now I'm O of 1, 2 milliseconds, I get my answers. This is an example of query that returns in 2 milliseconds, even if there's a billion documents in there, 2 milliseconds, right? For whom is that clear? Right? We have an index, it's the same predicates, 2 milliseconds. This one is not going to be instant because you have to first recognize you have the index on profession in that case, so you can pre-filter and only read the physicist, but you might still get a few of them. And the part with theories you need to do in memory, right? So you need to do a second filtering in memory based on the theories. So in that case, it's not going to be O of 1. It's O of 1 for the profession part, but there is extra work to do to filter also by theories. For whom is that clear? Right? In most of the cases, it's going to be like this. The index makes it a bit faster, but you don't always get something instant because there's extra work. Note that the range indices also work with multiple keys, right? So in that case, if I say birth and then death, it means that I first sort by birth, and if the birth is the same, then I sort by death within the births that are the same. And in that case, a query like this is instant. No, sorry, not instant, logarithmic time, because I just look up this compound key in my B+3, right? I can also swap this for a -1. In that case, I'm just saying that I sort by birth increasing, and within the same birth, I sort by death decreasing, right? Decreasing here. All right. And the beauty of these indices is that I can use ranges. So if it's a 1, so it's a B+3 index, I can have a query like this that is going to return faster than if I need to scan everything, right? Now, it's logarithmic time for the lookup, but if you're asking for half of the data in the collection, which might be the case here, then you still need a linear time, right? But it's not because of the index, it's because of the amount of the quantity in the outputs, right? So the complexity is always at least the size of the outputs, is what you learn in theoretical computer science. And you might have some post-filtering, because here I only index by birth, not by death, so it's additional. But now, this is a new insight. If I have an index on birth and then death, a query like this can also use the index. Even though the key is not exactly the same, I don't have the death in there, only the birth, but it works because, in fact, if I consider birth-death, birth 1887 is a range. It's all of the birth death that are born in 1887, no matter where the death date is. So this is why this works. So whenever you have an index, birth, death, like in that case, it would be totally useless to also build an index on birth, right? If I have an index on ABC, I don't need an index on A, B, and I don't need an index on A. It's a common mistake many people do, and they waste space on this because they build too many indices, right? So I'm going to stop here for today, and I'm going to finish covering indices next week, and then we'll look into query languages for nested heterogeneous data. Thank you very much. Enjoy the exercises, and I will see you next week for the continuation of the course. Thank you.